Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. Today our group will be presenting on the analysis of transfer function and the construction of plot for our advanced electrical circuit BRT 1333. Before we dive into the technical details, let me introduce our team's members from group 9. First is Muhammad Iman Hazid bin Muhammad Hakim. Next, me, Irdina Ashida binti Muhammad Nizam. Next, Wan Siti Nur Najla Aisyah binti Wan Ahmad Tajuddin, and lastly, Wardah binti Abdul Razak. We are from BERT. Okay, introduction to transfer function. So, to begin kita kena faham apa tu transfer function. Ia dilambangkan dengan sebagai H omega dan yang merupakan model matematik untuk describe bagaimana linear electrical network bertindak balas terhadap frekuensi yang berbeza. Ia juga dikira melalui ratio antara phasor output Y omega dengan phasor input X omega. Okey, kalau kita tengok persamaan kat bawah ni, H omega ada dua bahagian utama, iaitu first numerator and denominator. Zero are the root of the numerator that make the entire function equal to zero, and poles are roots of the denominator that make the transfer function reach infinity. So, kenapa kita kena gunakan benda ni? Why do we use this? This analysis is essential for three main reasons. First is it's allowed to use to analyze the frequencies response of any linear network. Yang mana untuk analyze respon frekuensi bagi sebuah linear network. Yang kedua adalah untuk menentukan to determine gain magnitude and phase shift, iaitu untuk menentukan nilai gain magnitude dan juga phase shift. Dan yang paling penting, it is essential for designing filter and control system. Dia sangat diperlukan bila kita nak design filter ataupun control system. Okay, now we have covered the basic. Kita akan tengok bahagian praktikal. Kita akan bincangkan satu soalan spesifik untuk tunjukkan macam mana nak kenal pasti poles and zeros ni dan bagaimana kita nak lukis spot plot berdasarkan data tersebut. Saya serahkan kepada rakan saya, Muhammad Iman Haziq, untuk jelaskan bahagian ini.
Assalamualaikum and greetings to our lecturer, Dr. Suraya, and also our fellow students. I am from Group 9, partaking the analysis of transfer function for question A and the magnitude plot for question G. So, I am Muhammad Iman Haziq Muhammad Hakim. Part of the Group 9 are going to explain how do we get the transfer function from question A and also how to convert from the magnitude plot from the question G to a transfer function. And also we have to construct the magnitude plot and also the phase plot by referring to the table of magnitude plot. Okay, without further ado, I'm going to explain for the first question, which is transfer function for question A. Given that 200 j omega divided with j omega plus 2 and j omega plus 10, we know that the denominator we have to factorize to get the Bode plot form, the standard Bode plot form, which we learned on chapter 4 previously. So we applied from chapter 4, we factorize the denominator. So we bring the constant number into the front. So which is we will get, the final answer is 200 j omega divided by 2 multiply with 10 and bracket j omega. We factorize the 2, so we get j omega divided by 2 plus 1, and also in bracket j omega divided by 10 plus 1. So following with, so we know that if we move the constant number 2 and 10, we can multiply it directly and also cancel down we from the top and the denominator. So after we cancel it, the denominator doesn't have any constant number, but at the top we have 10 as the constant number. So we can also determine the standard Bode plot form, which we know that the 10 will be k as the constant number and j omega will be zeros. How do I know this? How do I determine these numbers and also these zeros? So we have this word plot summaries that given from our lecturer, Dr. Suraya. So we know that if j omega, we will determine it as 0. And also for the denominator, we have j over z, or we call it as j over number plus 1, we call it as simple pole. So we have two of them. We can determine, we can actually put them as a simple pole and a simple pole. So we have 10 as our constant number k, j omega as our zeros, and two simple pole at the denominator. So now we can actually construct the magnitude plot. Okay, so without further ado, I will explain how do we construct our magnitude plot. So I'm going to explain for our magnitude plot. As you can see, before we doing our magnitude plot, we have 10 as our constant number. So how do we convert from that constant number into a magnitude plot standard form? So we have to apply the formula 20 log k, which is we substitute our constant number 20 log 10, we will get 20 decibel. That will be our zero. So as we can see, at the Bode plot summary, we have zero. We have zero line from our negative 20 dB. It will cross. It will cross over number one. It will cross over one. As you can see at the table, it's stated right here. Okay, so and we have constant number of 20 dB at k. As you can see at the plus 20 dB, we have k, a straight line, flat line. Okay, so after that, we have region. We have to divide by 3 region. So we know that the region 1 is divided from 0.1 to 2, and region number 2 is 2 to 10. And region number 3 is 10 and above. So between these three regions, we can determine the moving graph. So how do we determine moving graph? So we can see that simple zero stated that it will increase. A simple pole it will drop. Simple pole it will drop right here. As you can see, the simple pole it has minus 20 dB per decades. So the first our zero plot for the magnitude plot, the zero at the origin contribute a slope of plus 20 decibel per decade, which each pole contribute minus 20 decibel per decade. So we know that each pole, we have two poles. It contains the number one pole, as you can see at it cross. It's not crossing, but it start from 2. That is our first simple pole, and our second simple pole at 10. So the slope increase. For the slope, it increase at low frequency and become flat at the middle of region. So the first region it increase, and the second region it will become flat. At the third region, it will drop. it will decrease at high frequency. Yes, it will decrease from the flat, from previously. So it will be first one is increase, flat, and also drop, decrease. And I actually state how do we get the slope by by rewrite our moving graph. So we know that if starting we actually add 20 dB per decade, so it goes up, it goes increase. And for the second region, we know that we will subtract with 20 dB per decade, so it will be 0 dB, so it will be flat. And after that, for the second pulse, it has it's stated right here minus 20 dB per decades. So it drops for a high frequency, drop downs until the end. So that is for our slope. I will explain for the phase plot. Continuing with our phase plot for transfer function A, question A. So as you can see here, we know that we don't have any k constant value. So if we don't have any k constant value, we have to draw a straight line, a straight flat line at 0 degrees. At 0 degrees, that will be our first straight line. So for the second one, we know that j omega is zeros. So by referring to our Bode plot summary table, we see that zeros are actually a straight line starting from 90 degrees. So I'm sorry because this drawing is made with handwriting, so it is a bit unclear to see here, but I will explain briefly what I did right here. So don't worry. So for the second straight line, constant line will be j omega for our 90 degrees. So following by two simple pole. Okay, right here I will explain why our simple pole doesn't start at 2 radians per second. Okay, so as you can you have to differentiate the axis. So this is the degrees and this is the radians per seconds. So in phase plot, the phase change of a pole or a zero does not occur suddenly at the corner frequency. Instead, it is occur gradually over 2 decades, from 1 decade before to 1 decade after the corner value. After the corner frequency. I'm sorry. So let's take example. For our for the term j omega divided by 2 plus 1, we actually it shows that the corner frequency is 2 radians per second, but the phase change start at 0.1. So what we have to do is 2 radians per second multiplied by 0.1. So we will get 0.2 radians per second. So thus we will have the first phase plot starting at 0.2 radians per second and end at 20 radians per second. It is same as the next one, j omega divided by 10 plus 1. It is actually the corner value is 10 radians per second. So if the phase change start at 0.1, we have to multiply by 10. So our phase plot starting at 1 radian per second and end with 100 radians per second. So next, I will explain how our slope moving. So the first, we have 4 regions. As you can see, we have 4 regions. So it start at 90 degrees, it will go flat. It's starting for the starting, and it will drop by 45 degrees. And from the 45 degrees, it dropped 90 degrees until the negative 45 degrees, and it decrease gradually for 45 degrees, and it will end at 90 degrees, a negative 90 degrees. So that's all for our phase plot. I will moving for the next question. So for the question number 2, we given the magnitude plot for G. So as we can see here, it gives us the magnitude plot. So what we have to do, we have to convert this magnitude plot into a transfer function. So firstly, we have to analyze the BERT plot. Firstly, we can see that the graph is start at 20 dB, at the axis of 20 dB. So we know the constant number right there, the first constant number actually makes it start at 20 dB. And let's examine the slope after this. After that, let's examine I'm sorry. Let's examine the slope. So the first loop we have four regions because we have four regions. So the first loop, it is actually a constant loop, that determines our constant value, and it increase by 20 decibel per decade, and it goes flat and it decrease by 20 decibel per decade. So right here we can actually determine by looking at the slope. We have seen three different movement on our slope. So the first one is increase, the second one is goes flat, and the third one is decrease. So we can actually determine that if it's increased, what is it? By referring at our board plot summary, it is shown that simple zero for increasing of our magnitude plot. So the first one we know that the first movement we know that it is a simple zero starting at 10 radians per second, and it goes flat for plus for a positive 20 dB per decades. It goes flat because it minus 20 dB per decades. What 20 dB per decades? It is simple pole. So a simple pole starting at 100 radians per second. And for the last region, at 1000 radians per second, it is also decreased by 20 dB per decade. So it is also a simple pole at 1000 radians per second. Thus, we actually know that it doesn't have any zeros, it doesn't have any pole, it just have gain. It just have a gain, k. So how to determine the gain? So we know that actually we know that our formula is 20 log k, right? A 20 log k. We just have to move or anti-log, and we will get the gain k is 10. So our constant number for k is 10. And the tree movement shows that what is the what is our numerator and denominator. And for the first one, we know that the magnitude plot increased by 20 dB per decade. So it is a simple zero. So it is a simple zero. By taking the value of radian per second, we have our first value at zero at our numerator is j omega divided by 10 plus 1. And for our denominator will be both a simple pole because it is decreased by 20 dB per decades. So the first one starting at 100 radians per second, it will be j omega divided by 100 radians per second plus 1, and also the second one is j omega divided by 1000 plus 1. So there we have our transfer function for our question G. And I will go for our how to plot our phase plot after this.
Assalamualaikum. My name is Fantitin Nur Najla Aisyah binti Wa Ahmad Tajuddin. My matric number is B122420087. Today I will explain about of the plot. The figure represents a bird plot where the system responds with analysis in the frequency domain. The horizontal axis is the logarithmic frequency scale, while the vertical axis represents the phase angle in degrees. At low frequency, the phase type close to 0 degrees, which means the output signal is nearly in phase with the output. This indicates that the system behaves normally without much delay at low frequency. As the frequency increases and approaches the corner frequency, the phase begins to decrease gradually. Each pole in the transfer function contributes at -90 degree phase shift, and this change occurs smoothly over approximately 2 decades, from 1 decade before to 1 decade after the corner frequency. Next, I will pass the next explanation about this plot to Wardah.
Hi, my name is Warda Bita Braza and my number metric is B122420126. So today I'm going to continue this presentation. For this slide, the slope line indicates the phase transition region caused by the presence of a pole. The flat section indicates an almost constant phase angle. If more than one pole is present, the phase effects are combined, resulting in a larger phase drop, for example, minus 180 degree. At high frequencies, the phase angles becomes nearly constant at a negative value, indicating that the output signal lags behind the input signal.
For discussion, a bird plot is an important graph used in control system and signal processing to show a system behaves at different frequencies. It has two parts: a magnitude plot, which shows how the system gains change in the decibel, and phase plot, which show the phase shift in degree. By looking at this plot, engineers can find key information like cut-off frequency, gain margin, and phase margin, which help assess system stability and performance. But plots are often used when designing filter, amplifier, and control system, helping engineers understand and improve how the system works.
For conclusion, in this assignment, we were completely successful in creating Bode plot. A Bode plot is simply a graph that shows the magnitude and phase of a transfer function as the frequency changes. To cover a wide range of frequencies and magnitudes, we plot the logarithm of frequency and use a logarithmic or decibel scale for magnitude. The transfer function is a key tool in electrical engineering and signal processing. It describes how a circuit responds to different frequencies by showing the ratio of the output signal to the input signal. Using the transfer function, we can see the circuit's frequency response. First, how it amplifies or reduces signal at various frequency, and second, how it shifts their phase. This is very useful for designing circuits to filter certain frequencies, improve signal quality, or reduce noise. In short, transfer function is an essential tool for beginners and engineers, helping them to understand and control circuit behavior in the frequency domain and allowing them to design efficient and effective electronic systems. That's all from us for analysis of transfer function and the construction of body plots. Thank you.